Hey, welcome. It's another video. This one is about scientific notation. So we had our little scientist and he's shooting out some notation. We're not sure what he's saying, but we're going to try to make sense of it as we move through this particular little video. So in our lives, or in your lives, we're going to come across numbers, large numbers and small numbers. This is an approximation of how far it is from the Earth to the Sun, 93 million miles. Okay, 93 million miles, which isn't really that large a number in the scheme of things. This is the federal debt, this number right here, which is the amount of money that the government owes itself, sort of thing, or I guess we owe it to other countries, so we're in debt to other countries. And so it's, let's see, so there's thousands, there's millions, there's billions, and this is trillions. So this is $16 trillion, which is a lot of money. And then there's small numbers like the size of an electron. Okay, and this is actually, I didn't put the units, but this is in centimeters. So it's 0.000000000000281 centimeters. So scientific notation is going to allow us to rewrite those numbers so we don't have to write as many zeros, we don't have to write as many extra digits, and we still get the idea that it's a large number or a not so large number. So with scientific notation, we rewrite our numbers in this format. We've got some number that's between 1 and 10. It's at least 1, and it's not 10, so it can be 9.99999, whatever, but we can't get to 10. And it can be a decimal number, 3.52, 4.68, anything like that. So some number times 10 to some power. Okay, so this is a power, this is an exponent. Okay, so an example scientific notation, 3.58 times 10 to the 8th, we'll say. Might be a way to write a number. So that is in scientific notation. Let's see what we can do. So we're talking about the distance to the sun. Okay, distance to the sun. I don't know if I'm going to be able to grab over this. We're going to move this pointer. Should probably be able to get that back. I can. Bear with me for a brief moment. I want that. To go back to there. Okay. So what I want to do is I want to move the decimal point, just right here. And I want to move the decimal point until I get a number between 1 and 10. If I put it there, I don't have a number between 1 and 10. There, no. There, no. No. But if I put it right there, I have myself a number between 9 and 10. See it? What would that number be? That number would be 9.3. And so then, times 10 to the, how many places did I move the decimal spot? It was there, I moved it 1, 2, 3, 4, 5, 6, 7 places. So I moved it 7 spots, so my exponent is 7. So another way, and that's a really poorly written 7, but let's see what I can do better. Make it worse. 9.3 times 10 to the 7th power. That's another way to write 93 million miles. 9.3 times 10 to the 7th power. So we would say that as 9.3 times 10 to the 7th power. Okay. So there's another one. Let's try that second one. So this is a really big number. We already have a decimal point in it. And so the question is, where do we put the decimal point so that we get a number between 1 and 10? And so we just keep moving it over. No. You may get to the point where you realize, hey, I put it right after the first number. I get myself a decimal point there. So with scientific notation, we tend to use the number and probably 2, maybe 3 decimals after. We don't, to write out 1.674227527418597 doesn't really save us anything. So we're just going to say 1.67 times 10 to the, how many places do we move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spots. So 1.67 times 10 to the 13th dollars. It's an approximate number at this point, and since I got that number off the internet, it's changed certainly because we go further and further into debt all the time. All right, so Find a number between 1 and 10. How many places do you have to move the decimal place over to make it work out? All right. So here we've got a really small number, so it's going to be the same sort of process. We just have to notate it a little bit differently. So again, we're looking for that place to move the decimal, so we get a number between 1 and 10. Stop me when I'm there. Oop, all right, there it is. So right there is where I would put my decimal point. Okay, and so the number that I would get, 2.81. 2.81. How many spots did I move my decimal point? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 2.81 times 10 to the 13. But we moved it in the other direction. We moved it for a small number, so we moved it to the negative 13. 2.81 times 10 to the negative 13. So when we have negative numbers as our exponent, it means we've got a really, really small number in scientific notation. 2.81 times 10 to the negative 13. Okay? So we've been talking about rational and irrational numbers. When I have a number in scientific notation, is it rational or is it irrational? Good question. Well, could I put this number precisely on a number line? If I had to find enough grain number line, sure. Could I put that number precisely on a number line? 1.67. I mean, I certainly could put this on a number line, right? The original number. Can I put 93 million miles exactly on a number line? Sure. So typically with these scientific notations, it's a specific number that we're talking about. So these scientific notation numbers tend to be rational numbers. Okay? I guess if we had pi to some power, then maybe not. But for the most part, we're dealing with them. They're going to be rational numbers. So here's a question for you. What happens when I add a couple scientific notation numbers together, or I add a couple of rational or irrational numbers? So if I take m and I n, notice they have the same base number, okay, 10 to the 6th. So my answer is going to be something times 10 to the 6th. Then I would just need to add up the two outside numbers, 4.57 plus, 4.29 plus 4, those two numbers there, you see them. And so 7 plus 9 is 16, 1 to carry, that's 8. And 3 and 4, so we didn't need to carry anything, it's 3 and 4 is 7. So this would become 7.86 times 10 to the 6th power if I add those two numbers together. And since we started with a rational number, we added another rational number to it, we ended up with another third rational number. Okay? If I tried to add n and p, I can't really do that directly because they have different exponents. Okay? We could do it. We'd have to, turn one or the other into 10 into the same base. We need to have that same exponent here. So if I could make this into 10 to the 6th, we'd be okay with that happening. Okay? But for the sake of what we're saying now, is that they don't have the same basis, so we'd have to adjust and have same exponent. So we couldn't easily add them together. We could do it, but we're not going to worry about that right now. We could do m times n. Okay, m times n. Here's the thing: if you remember, when you're multiplying with exponents, I've got 10 to the 6th times 10 to the 6th, and so what we do is we add the exponents together. Okay, don't worry too much about that if you don't quite remember. It's not really the point here. So this becomes 10 to the 12th. And then we would multiply 3.57 and 4.29. So I end up with, when I multiply those two numbers, I end up with 15.31 times 10 to the 12th. Okay, but I've broken my rules for scientific notation. Hopefully you caught that, because I get a number that's bigger than 10 here. So what I need to do is I need to make this 1.531 times 10 to the 13th. So I move the decimal place 1 over. Okay, so I add 1 to the exponent. So when I multiply them that way, that's what happens. Okay, you can try m times p if you want. Give that a shot. Tell me what you come up with when I see you next, just as a way of getting some information from you. All right, so a couple of questions for you to leave here with. If we add a couple of rational numbers, do we get a rational number or an irrational number? Okay, so think of cases where it works. Think of possible ways that you could make it not work. Okay, if I add two rational numbers, do I get a rational number? Do I get an irrational number? If I add two irrational numbers, what happens? Okay, so if I add two irrational numbers, do I get a rational number or an irrational number, or possibly it could depend. the easiest irrational numbers are like, the square root of 7 and the square root of 11. I don't know, something like that. Do I end up with a rational or irrational? And then the other way is, what happens if I add a rational and an irrational number together? Do I end up with a rational number, or do I end up with an irrational number? See what you can think of on those. Perhaps come up with some examples. Same questions, but this time with multiplication. And I'm just going to ask you, and we'll see if we can chat about them a little bit in class when you're ready. If I multiply a couple rational numbers, what do I get? Another rational number or an irrational number? If I multiply two irrational numbers, what do I end up with? A rational number or an irrational number? And if I multiply a rational number and an irrational number, what am I going to end up with? Rational, irrational, or possibly for any of these, the answer could be, it depends, Mr. Take. All right? So just trying to, a way to wrap us back around to rational and irrational numbers while talking about scientific notation at the same time. That, I guess, is the end of our little story for today. I appreciate you stopping by, and we will talk to you soon. Hope you learned something.